Well, if we want to do multivariable calculus, we've got to talk about vectors, so let's take a look at the ideas as well as the various notations and definitions behind vectors. Basically, there are two kinds of quantities in physics, scalars and vectors. And scalars are quantities that only have magnitude, so those are things like temperature, mass, volume, or pressure. These are all quantities that can be measured at isolated points in space, and we just get a number. However, there are also other important physical quantities that are vectors. And vectors have magnitude and direction. So examples of vectors are the velocity, the force, or the magnetic field. And so, for example, here we have an image that is courtesy of Louisiana Tech University that I'm using with permission. If we're talking about force as a vector, well, in volleyball, for example, when you spike a ball, then basically with your hand you apply a force to the volleyball, which ultimately changes the velocity of the volleyball, preferably towards the ground of your opposing team's part of the field. And, well, those are all quantities that must have, where the direction is very important, right? Because if this force is applied incorrectly, then the spike goes out and the opposing team gets a point, whereas if it's applied correctly and the spike is successful, your team gets a point. Okay, so aside from magnitude, it is also for many quantities important to record the direction. And so the question becomes, how do we do that? Well, if we're representing vectors visually, we would represent vectors as arrows, and the length of the arrow gives the magnitude, and the direction of the arrow gives the direction, where a little duh may be in order for the second part of that, right? I mean, what else would the direction of the arrow give but the direction of the vector? And we do not specify a starting point for the vector or a point of action. So if we go back to the volleyball example, the same force applied to the ball or whiffing in the air would be the same force with drastically different consequences, right? One of them could be, even if a spike is set up on the second hit, that it was maybe a deliberate miss in order to confuse your opponent, but either way, the force may or may not apply to the ball, depending on what the point of action of the force is. It turns out that for the development of theoretical mechanics, the point of action is really not that important. In fact, it's more information than we would conveniently carry through the development. So visually, for us, a vector is going to be an equivalence class of all arrows that have the same direction and magnitude. So that means if this is a vector, then this arrow is also a representative of the same vector, and so are all these other arrows here. Okay, so if a point of action is not given, we will typically start our vectors at the origin. That's going to make computations as well as representations easier. And we will, in particular, talk about position vectors, and we'll do that later. But after all, if we just draw our XYZ coordinate system, then basically the most natural representative for a vector will be the representative that starts at the origin. And if that is the vector 1, 2, 3, then we also have the same problem as we had for representing points. We can't quite see in the picture which direction this vector is pointing, and so if we need to make that explicit, we would draw the endpoint just like we draw a point. We would go down to the xy plane and then over to the x and y axes, and we would, of course, the point that is projected down is the one corresponding point with z coordinate 0, so that would be the point 1, 2, 0 down here. Okay, so we only need the endpoint to specify these kinds of vectors that start at the origin, and that is the key to vector notation. So a vector in n-dimensional space is given as a column, or a column vector, and that's v with an arrow on top, where the column is just v1, v2, all the way through vn, where these things are called the components of the vector. And it's also denoted as left bracket, or left angle, v1, v2, all the way through vn, separated by semicolons. So those are n numbers, and those numbers are called components. Well, okay, so we're looking at n dimensions again, and vectors will usually be denoted by letters with a vector arrow on top. We're looking at n dimensions here, but n dimensions are just a general way to treat the more familiar settings simultaneously. So a two-dimensional vector is a vector v1, v2, or v equals xy. And a three-dimensional vector is a vector v1, v2, v3, or v equals xyz. I just didn't want to do two separate definitions. This is a two-dimensional vector. This is a three-dimensional vector. Let's think of these things always in arbitrary dimensions, and if arbitrary for you just means 2 or 3, that's okay also for most of what we're going to do in this course. Okay, so the interesting thing now is certainly if we wanted to consider four-dimensional vectors, we could do that too. Addition of vectors, so now we're talking about vector algebra. Addition of vectors models the addition of forces. And so if, for example, again we're going back to volleyball, if you are setting a ball in volleyball, then technically you're applying a force with your right hand and with your left hand, and there are certainly rules that say that you can only do that in certain ways, namely the contact has to be simultaneously. But technically you are applying two forces here. This is again an image courtesy of Louisiana Tech University that I'm using with permission. And well, so what that means is if I've got a vector A here and a vector B here, the addition of forces is, as people teach you in physics, that you just draw these vectors into a parallelogram. Basically, you draw a dashed vector that is parallel to A and has the same length up here, and you also tack a copy of B on here that makes a parallelogram, and then the sum is the diagonal of this parallelogram. And we're going to see how that works with the components after we are through all the definitions. We also want to multiply vectors with a scalar, and that should just stretch a vector. So if I've got a vector here, then a scalar multiple of the vector ought to be a longer or a shorter vector that is just lengthened or shortened by the stretch factor that is given by the scalar multiple. Okay, so in terms of defining that, we let C be a real number, a scalar, and we let A and B be vectors with components A1 through AN and B1 through Bn. And we define A plus B to be A1 through AN plus B1 through Bn, which is just A1 plus B1, A2 plus B2 through AN plus Bn. And C times A is C times A1, A2 all the way through AN, which is just CA1, CA2 all the way through CAN. And those are very nice mathematical definitions. You can also see here a potential advantage of the column notation, which is definitely native to linear algebra, which is a very important field in mathematics. The column notation is kind of nice because addition is just going straight across, and multiplication, except for the fact that you have to, of course, put the C into every component, is also pretty much accomplished by going across. However, we said that this addition here was supposed to have something to do with parallelograms, and that's not necessarily easily visible here. So let's take a look at that in an example. And the example is just very simple. We want to add the vectors 1, 2, and 3, 1. And what would that look like? Well, here is a two-dimensional coordinate system, so we'll freely work with two-dimensional vectors, three-dimensional vectors, whatever we need. And, well, here's the vector 1, 2, and that's A. And here's the vector 3, 1, and that's B. And now if we were to do this with the parallelogram, well, we would take a copy of B, put it over here, take a copy of A, put it over here, and the sum would be the diagonal of the parallelogram, which would be the vector 4, 3. And of course, that's exactly what we would get if we take A plus B being 1, 2 plus 3, 1. Well, that's 1 plus 3 and 2 plus 1, and that's 4, 3. So basically, this idea of adding components is exactly what takes the vector B, adds it onto the end of vector A in order to get A plus B as what is the diagonal in this parallelogram. All right, and similarly, of course, the multiplication also stretches or shrinks the vector. We don't give an example for that. That's just pretty easy anyway. If we're going to subtract vectors, well, we've got 3 guesses what to do, and it's not that hard to see, right? If I want to subtract B being 2, negative 1, 6 from A being 5, 2, 4, well, A minus B is 5, 2, 4 minus 2, negative 1, 6. 5 minus 2 is 3. 2 minus negative 1 is 3. And 4 minus 6 is negative 2. And that would be subtraction of vectors, which technically actually is that we add negative 1 times the second vector. But we can see that even without a formal definition of subtraction, things work out pretty much as they should. And we could give a formal definition here. All right, what else do we have? Well, we can talk about parallel vectors, and so two vectors A and B are called parallel if and only if there is a number lambda equals 0, so that A is lambda times B. and that is the vectors are parallel if and only if they are multiples of each other. And sometimes parallel vectors for which lambda is smaller than 0 are also referred to as antiparallel, because basically what we have is that if we've got two vectors like this, they're called parallel. One is a multiple of the other. If they stand like this, then the long vector is still a multiple of the short vector. It's just that you need a negative factor, and that's what we sometimes call antiparallel. And then, of course, there's also a situation where this vector is not a multiple of that vector, and we call that not parallel, of course. Okay, so if we want to do this with numbers, we could do something like this, where we just determine which, if any, of the vectors a equals 1, negative 2, b equals 3, 5, and c equals negative 6, negative 10 are parallel. And, well, we just set up, okay, are a and b parallel? That would mean that a is lambda times b, which would be the same as saying that 1, negative 2 is lambda times 3, 5, which would mean that 1 is lambda times 3 and negative 2 is lambda times 5. And you can see that that has no solution, because we would get lambda equals 1/3 from the first, and that is not going to solve the second equation. Okay, so there's no solution, so a is not parallel to b. A being lambda c would be what we would have to check out to determine whether a is parallel to c. And that's the same as saying that 1, negative 2 is equal to lambda times negative 6, negative 10, which is the same as 1 being lambda times negative 6, right? We look at the x components, and negative 2 being lambda times negative 10, and that would be the y components. And if we solve that, we get lambda equals negative 1/6, and again, lambda equals negative 1/6 does not solve the second equation. So again, we have no solution, and a and c are not parallel. Well, finally, we have to check if b and c are parallel. So we set up b equals lambda times c. That gives us that 3, 5 would be equal to lambda times negative 6, negative 10. So the x components would give us the equation 3 equals lambda times negative 6. And the y components give us the equation 5 equals lambda times negative 10. And if we solve that, we realize that lambda equals negative 1/2 actually solves both equations. And that means that b is parallel to a because b is a multiple of a. And if we want to be really specific, because the multiplicative factor is negative, we would say that b is antiparallel to c, and that's the only parallelity that we have between any of the vectors in here. Okay, notation for vectors is always something that takes a while for getting used to. However, it's not something that we should worry about too much. So, we did not formally define how to divide a vector by a number, and that's because in abstract settings, it's just more sensible to work without a formal notion of division. Basically, division in abstract settings gets so problematic that ultimately you just don't want to deal with it. And so for us, any notation v over h, vector over a number, where v is a vector and h not equal to 0 is a number, means that we just multiply the vector with the reciprocal of the number. So that means v over h will be 1 over h times the vector v. So here we're towing the line between correct abstract definitions and expediency and just usable notation. Of course, we're going to every so often have these kinds of fractions, and if we wanted to be totally careful, we would say, well, it just means that 1 over h is multiplied with v. All right, magnitudes and unit vectors. Well, sometimes it's easier to report magnitude and direction separately. That is something that happens very often in physics. So, for example, the gravitational force that the Earth exerts on your body has magnitude, force equals mass times gravitational acceleration. We know that. Where m is your mass, and g is the gravitational acceleration of the Earth. And the direction of the force is down. Whatever down means, it would be down towards the center of the Earth. And so we need to encode that direction somehow, because eventually when you're looking at scales where you look at several locations on Earth, all of a sudden down here and down, okay, here being Ruston, Louisiana, as this is being recorded, and down in Australia are two different vectors. They have totally different directions. So we're going to talk about the magnitude, and the magnitude or length or norm, and it's called v norm of a vector v, where we've got the components v1 through vn, is defined to be v norm, being the norm of v1 through vn, which is just the square root of the sum of the squares of the components, which is just the square root of v1 squared plus v2 squared plus and so on plus vn squared. Yeah, there should be a plus in there, but we're not going to worry about that right now. Well, it's also quite common to use absolute values for the magnitude. What we can already see here is if this vector is placed at the origin, then this magnitude really is the distance of the tip of the vector from the origin, which means it also makes sense to call the magnitude the length of the vector. And norm is basically notation from more advanced mathematics classes in linear algebra or in functional analysis, where also this notation of the doubled absolute value signs is more common. So this is a little bit idiosyncratic. In many calculus presentations, you will find the magnitude denoted with absolute value signs. I just like to denote the magnitude of a vector with a norm notation. In physics, the magnitude of a vector v is often denoted by the same letter, only without vector notation, and we're going to talk about that a little bit more also, because there is a lot of notation out there and we just need to be aware of it and then just go ahead and move on. And well, so for now, the following notations are used for the magnitude. On one hand, v without vector notation could be the norm, or it could also be v with absolute value signs being the norm. Alright, so in 2 dimensions, the norm of the vector xy is the square root of x squared plus y squared. In 3 dimensions, the norm is of the vector xyz is the square root of x squared plus y squared plus z squared. Again, we're stating it for n dimensions, and we know what that means then for 2 and 3 dimensions, and don't have to worry too much about memorizing separate formulas. Okay, example, well, compute the magnitude of the vector a equals -1, 5, 3. What are you going to do? You're going to square the components, add it up, and take the square root, right? Norm of a is the norm of -1, 5, 3. It's the square root of -1 squared plus 5 squared plus 3 squared, which is the square root of 1 plus 25 plus 9. That ends up being the square root of 35, and that's it. So we're mainly, we need to memorize these formulas. We need to know what the magnitude of a vector is, and we know what it means. It's the length. What can we do with magnitudes? Well, if we're looking at a 1.5 meter long bowstring that is pulled by a force of 250 newtons and makes an angle of 45 degrees against the vertical direction, well, let's take a look at what that looks like. So we're apparently having an application problem. Of course, this is a problem that I made up, but it's fairly realistic. Bows and arrows are a weapon for hunting, as well as other things that are not as beneficial for human health as hunting, that go across cultures. So this, for example, is an image of a Rikbakta archer who competes in the Brazil's indigenous games. The source is given here. The image was made available under a Creative Commons license that requested attribution as well as posting of the link to the image. The author is Walter Campanaro at Agência Brasil, and it should always be said that was part of the license. Endorsement is neither claimed nor implied. I just am using the picture in accordance with the license, and basically what I'm trying to say here is, yeah, I mean, we can set up some pictures that are some problems that are fairly natural now, because if you're looking at that arrow, and if you compare that to the height of a human, if you look at that bow and its string, and if you compare that to the regular height of a human being, a 1.5 meter long bowstring is quite realistic. The force of 250 newtons, that is something that I looked up, and archers can pull with that force and even with larger force. And a 45 degree angle against the vertical direction, well, yeah, it's not quite 45 degrees. I wasn't there to have the gentleman turn or anything like that. But a 45 degree angle of the bowstring against the vertical direction is also something that is quite realistic. And so when we have that, we can ask, for example, what the tensile force within the bowstring is. And so that means we would assume that the arrow is knocked in the center of the string, right? That's another thing that can be slightly off, but all of a sudden we can take this beautiful picture of this archer and turn it into a mathematical model where here's the top, where the bowstring is fixed, here's the bottom where the bowstring is fixed, and here's the bowstring itself. And we again see the power of mathematical modeling, because the bow itself is actually not relevant for the computation. What we need is a solid fixture for the bowstring itself, and then an image of the string. What we know is that there is a force that is pulling back, and that has magnitude 250 newtons. We know that the angle against the vertical of the bowstring is 45 degrees on top and on the bottom. And now what we need to do is we need to decompose this force, which is 0 and negative 250, and that should actually be negative 250 and 0 because it's a force in the negative x direction. Okay, so we're back, and here's the typo fixed. The vector is negative 250 in the negative x direction, and then y is this, so we're actually having, if we're thinking about z at all, then z is coming towards us here, very much like it would be done in physics. And this force needs to be compensated, of course, by the tensile force within the string. Otherwise, there would be motion, there would be things shivering and the like, which you don't want to have when you're shooting an arrow. The string force, the tensile force, has to be parallel to the string, and that means that it's got to have a component that is parallel to the vector 1, 1, which is a 45-degree angle going up, and the vector 1, negative 1, which is a 45-degree angle going down. And so this is now, even though it's written in vector form, it's a system of two equations in two variables. So we are done with the modeling. Now the rest is just computation. The rest is just mathematics. So here we go. Here's the equation. That means negative 250 is a plus b. It means 0 is a minus b. If we add these two equations, we get that negative 250 is 2a. That means a is negative 125. And that means b is also negative 125 because a minus b is 0. And that means that the tensile force, well, the tensile force, if we're looking at just the magnitude, because again, the tensile force is always parallel to the string that is being tensed, and so what you really want to report is the magnitude, because the direction is always parallel to the string. And so you need the magnitude of the vector negative 125 times 1, 1, and that would be 125 times the square root of 1 plus 1, and that's 125 square root of 2, which is something that if you need more decimals you can work out. We just put the unit of newtons behind that because everything was done in newtons, and that solves the problem. So this is something that is certainly made up, but it is a realistic problem because people who make bowstrings have to make bowstrings that stand up to the tensile forces that are to be expected within the bow, and probably a certain safety margin, and so on and so on. Okay, so that was magnitudes. What about directions? Well, a unit vector is a vector of length 1. And so basically unit vectors are pure directions. If I want to give you something that just has a direction, I can't give you a direction without magnitude, because as soon as we have an arrow, the arrow will have a length, and so the convention then is that we use unit vectors where the length is 1, which is basically the length that is to be disregarded, if you will. Okay, so if v is a vector with length not equal to 0, then the vector u being 1 over v norm times v, which is v over v norm, that's a unit vector, and that's fairly easy to prove, because if we take the norm of 1 over v norm times v, then that's the norm of 1 over v norm of the column vector v1 through vn, which would be, if I put the 1 over v norm in here, I'm just going to use all the operations that we know so far that are allowed. I can multiply every component with 1 over v norm. Then I use the magnitude formula, because now I have just directly the magnitude of a vector, and I get the sum of 1 over v norm times vj quantity squared. Okay, so that gives me a sum of 1 over v squared times vj squared. And now the 1 over v norm squared can be pulled out, so that's 1 over v norm times the sum of the vj times the square root of the sum of the vj squares. And that's of course just 1 over v norm times v norm, and that's 1. And so that is similar to some of the proofs, one of the proofs that we did in the previous presentation, which is that you want to be able to follow these kinds of presentations to see that yes, every operation was allowed. We have all the requisite definitions in place, and well, then we move on and we continue applying things. And well, yeah, let's finish out our discussion of magnitudes and unit vectors by revisiting gravitational force. The gravitational force that acts on your body actually is F equals m times g times negative r over r norm, where r is a vector from the center of the Earth to your current position. The quantity r over r norm is a unit vector pointing from the center of the Earth to your current position, and the negative sign makes sure that the force points towards the center of the Earth and not away from it, meaning it points downwards. Now, when we express a gravitational force like this, we usually work on a scale that is large enough that we should actually use Newton's law of gravitation. So then we should write that the gravitational force is gravitational constant mass of the Earth times your mass divided by your distance from the center of the Earth divided by that times this unit vector that points towards the center of the Earth. This is the kind of thing that you often see in physics texts. You will also see in presentations in this class, and it's basically something where we separate magnitude from direction. Okay, the standard unit vectors are I being 1, 0, 0, j being 0, 1, 0, and k being 0, 0, 1. So if we're looking at a regular coordinate system, x, y, z, right-handed, here's I pointing in the x direction, j points in the y direction, and k points in the z direction. And yeah, that's already it. Those are the standard unit vectors that are very, very common throughout mathematics and physics. So as an example, the vector 3, negative 1, 2 could also be written as 3i plus negative 1j plus 2k, because that's how those components can be broken down. Now, the primary advantage that I can see in the ijk notation is that you can turn things into inline formulas, which means, at least to me, and I apologize if I'm stepping on colleagues' toes or so, but at least to me the primary advantage is that you can write things on a line, and that is really not something that should concern us. Column vectors are what we use in linear algebra, and column vectors are typically what people use in lengthy and ugly computations, and so we will stay with column vectors. You just need to be able to translate the ijk notation whenever you run into it. And yeah, okay, if you write that out and absorb the negative sign, that's 3i minus j plus 2k. All right, position vectors. Well, for the point p equals p1 through pn, the position vector of p is just p1 through pn as a column, so there is not much of a difference between points and position vectors. In fact, there's more of a formal difference. We haven't defined arithmetic for points, we have defined arithmetic for vectors. That's why we ultimately want to work with position vectors. And as a notation, well, we will usually denote the position vector of a point with the same lowercase letter, but in vector notation. So the position vector of the point P will be denoted by vector P. More notation, and I think that's what we're actually already going to close with. There are lots of vector notations, and that can be intimidating at first, it can be confusing at first, and it shouldn't be. The main piece of advice I have for you is look at what the author is using and then stay consistent with that notation, or convert it back to a notation that is more convenient for you. But basically, we use arrows on top of letters to indicate that a letter denotes a vector. So V arrow is a vector. Well, oftentimes authors use boldface letters to denote vectors. That is, in many texts, boldface V is a vector. In physics, apparently, that's something that just a colleague told me, hats are often used instead of arrows. So that means in many physics texts, apparently, V hat is a vector. In advanced math texts, vectors are just denoted simply with a letter, and so V is a vector if the author said so, and there's the underlying assumption that the reader will remember that. So that's 4 different notations for vectors, including some things that clash, because remember, in physics the convention is that the corresponding letter without vector notation is actually the magnitude. We use column vectors to record the components of vectors. To save vertical space, we'll sometimes write the vector xyz as bracket xyz. Some authors also use just parentheses xyz, and then the semicolons rather than commas are supposed to distinguish the vector from the point, which is getting a little bit too detailed for me. If I have to look at whether there's a semicolon or a comma, I'd rather write things out in column notations. Every so often we simply have to go here because you know that vertical space is limited on these slides, and I can't just put a column vector in and then not be able to present everything I want to present on one slide, because sometimes we just want to see everything in one place. So those are the notations that we will use. Well, the standard basis vectors I, j, k are also often called in this order E1, E2, and E3. So not to mention that the components could also have i's, j's, and k's tacked on. They could have E1s, E2s, E3s tacked on. I've seen texts in which these unit vectors are U1, U2, and U3. And so basically, as you read a text, check what notation or notations people are using and pretty much just make friends with those notations in the text you read and in the classes you take, but don't get too attached to those notations and don't put too much stock into them, because basically if we're looking at a final example here that I really have to say I've made deliberately inconsistent. Suppose somebody tells you that for the vectors a equals 2i minus j plus 5k, where vectors are denoted boldface, and the vector b hat, which is denoted with the hat notation and the angle notation, left angle, -2, 3, -1. I want to find the linear combination for b arrow minus a arrow. I mean, basically, I've tried to mix it up as much as possible, and I'm also sneaking in here the definition of a linear combination. A linear combination is whenever you multiply vectors with numbers and then add and subtract. Well, look, I mean, it doesn't matter what the notations are. As long as we can read those notations, we realize that 4b minus a is just 4 times the column vector 2, -1, 5. 4 times the column vector 2, 3, -1, because we're looking at 4b, minus a, so minus the column vector 2, -1, 5. Sorry about that, I looked in the wrong place. And if you work that out, well, 4 times -2 is -8, minus 2 is -10, and the other ones work similarly. 4 times 3 plus 1 is 13, and -4 minus 5 is -9, and that ends that one. So, another one that hopefully wasn't too bad, and that's good. Work your way through the homework, make sure that you are on top of the vector notations. Things will gradually get more challenging, but the main thing really is we need to make sure that we lay this foundation correctly so that we don't get tripped up by too many numbers, too many symbols, strange notations, and so on as we proceed. Next up is scalar products. I'll see you there.